ITOxygen is a multidisciplinary student enterprise at Michigan Technological University that specializes in information technology and leading edge software algorithms. We have had many projects this year, such as our AI onboarding project, which introduced people to how AI works through designing a screen scraper for a popular game streamed on Twitch, as well as having red and blue security teams, operations, and other such groups. Our selected project for this year's Design Expo was our weld identification algorithm. Missed welds pose a huge safety and liability risk for manufacturing. In the past 3 years in the auto industry alone, there have been vehicle recalls affecting over 10,000 vehicles from major brands like Chevrolet, Lexus, and Jaguar over mixed welds. In the spring of 2020, a leading design and manufacturing company contacted the ITOxygen Enterprise and asked the question, can we detect welding patterns, including missed welds and other items with data currently available and collected on a welding machine? We accepted this challenge and started looking into the problem and possible solutions. Within weeks, we determined a problem statement that would lead our development goals and priorities. Our sponsor requested an algorithm to detect missed welds, which could save users of said algorithm time and money and needed items like inspection, quality checks, and liability costs. We started looking into the limitations and the real-world impacts of this project. One of our first goals was to calculate the true cost of a missed weld, which is very hard to do because there are several places in the manufacturing process where it can be caught. If it is caught by the welder, it can be fixed rather easily with little cost. These costs will cost the company around 2 or 3 times the original cost of the weld, but if not caught by the welder, the prices can quickly skyrocket. If it is caught later in the manufacturing process of the part, the weld can still be fixed, but depending on if the company employs lean or just-in-time manufacturing processes, this can create a bottleneck, leading to hidden costs as well as the cost of fixing the weld. If the part goes a few hours before detecting the missed weld, the part may be getting painted in a paint line as part of an assembly or in other steps of production. And if it's determined here that there is an issue, there's a significant labor cost to both take apart the part and re-prepare the piece to be welded, as well as other impacts on manufacturing. The next part of manufacturing is in final assembly, and if caught here, the assembly would have to be completely torn apart, or the company would have to have extra equipment on hand to fix such issues as a missed weld, leading to significant time and capital investment. And if the part gets out of the factory, the cost will skyrocket even more, from hundreds or thousands of dollars to hundreds of thousands or even millions of dollars in field issues, recall, or possible liability claims and lawsuits. Due to this escalating cost of the need to fix the weld, we determined that this algorithm needed to be near real-time, easily scalable, and able to run on a welding machine, in the cloud, or on a production supervisor's computer. Some current systems existed to catch missed welds. However, they typically rely on extra interaction from the welder, such as pushing a button indicating when a weld starts or when a new piece will start, these are run on external units, which furthermore lead to additional costs for companies. As we went into working on this solution, we immediately identify that Python should be the programming language of choice for building such an algorithm. We discussed various choices for development, such as having some parts of the algorithm be in other languages, however found it was best to keep everything in Python, as there was no real slowdown with more modern libraries that Python supports, that support things like vectorization and other ways of iteration through data structures and arrays. Based off of our research and some initial prototyping, we came to the conclusion that we could make use of a machine learning algorithm that would suit well for our problem. Due to client confidentiality, however, we are not at liberty to discuss a more detailed information about the design of the algorithm. With the algorithm having a potential for a very large code base, we implemented Git control via GitHub very early on in our project, which helped with various tasks and branches to be worked on simultaneously. We then merged them together, bring everything down to a central repository, as well as having a history of nearly 100 various algorithms and solutions that we tried throughout the course of this project. Our algorithm can catch these errors in near real time using a state machine with artificial intelligence algorithms to group and classify welds, to catch missed welds and non-normal welds, while also having the potential to catch extended periods of downtimes like tip replacements and other issues, all to be forwarded to the production supervisor or any other person overseeing the algorithm to be able to catch errors before they impact the factory. Due to how we were able to design this algorithm can be used in any industry that welds with a specific set of welding machines, as this algorithm was made to work on any subset of data that the specific machines collected, and can be used with all welding purposes and processes that the machines are capable of. Due to this, we found our algorithm and welder's error were roughly 4% of all parts. That means the algorithm could correctly label 96% of parts that were provided by our sponsor. While our algorithm has been designed to work with any subset of data that welding machines can collect, there are limitations to what it can detect. In creation of our algorithm, we needed to determine a minimum floor of what we considered a new part while detecting it. As a result, there needs to be a minimum of 3 nearly identical parts welded in the file or data it examines. If there are not 3 nearly identical parts, the machine still has the potential to have the parts be identified, however, it is significantly less accurate. This algorithm can be run on data in multiple ways, and in order to adapt it, we worked with our sponsor to produce a standalone executable file from our Python codebase that could be used wherever and analyze past data. This executable file was made in order to help with initial implementation and buy-in from people throughout the company. This allowed our Python files to be ran with a single executable and not require an environment setup that would be common with Python applications. This also significantly simplified user interaction in the development stage, as all of the user input is packaged into a GUI, which allows them to select both the file and gives them where the output file will go. We also created a log file in addition to the Excel sheet output that can be looked at for advanced troubleshooting or if our algorithm is less accurate than expected. We are able to create various forms of documentation for the company outside of the standard best practices for Python. We are able to create external pages with method implementation, various flowcharts of the algorithm at different points, videos for both the users of the executable, as well as documentation on why we did what we did, with past algorithms that we used that were determined to both work correctly and not correctly, as well as various other methods for the software team to take a look at as they take the project on. This was all accomplished with the goal of being able to hand off said project to the team that we worked with to fully maintain, implement, and upgrade it in the future. Overall, our algorithm has the potential to save companies significant time, money by detecting missed welds in near real time. Through careful design thinking and the use of advanced artificial intelligence algorithms, we are able to create a scalable and adaptable solution that can be used across a variety of welding processes and machines.